Hello, everybody. My name is Matthew Hepworth, and I'll be doing some lesson 4 practice problems for the extra credit assignment. And so I'm going to start this video off by doing the lesson 4 problems with the solutions, and I'm going to go through it step by step, and I'll show you how to do it. So problem 1 states a true breeding pea plant with round and green seeds was crossed with a true breeding plant with wrinkled and yellow seeds. Round and yellow seeds are dominant traits. F1 plants were allowed to self-fertilize. What are the following probabilities for the F2 generation? Assume independent assortment for the two traits. And so up here, well, we'll just follow my mouse here. So up here I designated a key. So we have big R is round, which is dominant, and little r, which is wrinkled, which is recessive. And then the big G, capital G, is yellow, which is dominant, and then little g is green, which is recessive. And so I did the parent generation, which you have a true breeding dominant plant, or true breeding round and yellow plant, so capital R, capital G, time or against a true breeding wrinkled and green, which is represented right here. And then so across these, and this is the F1 generation that I got, and then I crossed these, and then I allowed these to self-fertilize. And so how I did this is I did a fork line method, so I drew out the traits individually. So R, little r, and that's how I did the crosses, and that's how I came up with these probabilities right here. It's a very simple method. And so here are the probabilities of all the F2 generation. And so we're talking about probabilities here. So for problem A, it asks what's the probability of an F2 plant that is wrinkled with yellow seeds. And so kind of following this, what I did is I followed the key up here, and I gave their genotypes. So wrinkled would have to be little r all the time, and yellow seeds, so they can be dominant. And so you have which is right here, which is represented by little r, big G, and then little r, big G, and that's a 3 out of 16, which is 18.8%. So all I did was just add these two together. And then for part B, it states that 3 out of the 3 F2 plants are going to be round with yellow seeds. So I found the probability of getting finding a plant that has round and yellow, that is found in red and yellow, or sorry, not red, sorry, round and yellow seeds. And so the genotypes represented right here: big R, big G, big R, big G, big R, big G, and big R, big G, little g. These genotypes are all representative of the round and yellow seed phenotype. And so there's 9 out of 16 of them. And so what I did is I raised it to the 3. Or if you want to think of it in more simpler terms, I didn't write it out here, but I'll just say it is like 9 to the 16th, 9 out of 16 times 9 out of 16 times 9 out of 16, or simply 9 out of 16 raised to the third, and I got 17.8%. And then C states F2 plant is either round, or is going to be either round or yellow, round and yellow, either round or yellow, or green or wrinkled. And so basically I found all the number of phenotypes, or the number of genotypes that correlate with this particular phenotype right here. And I got 9 out of 16 just following this chart right here and following this key. And then same thing with the green and wrinkled. And so I added them together because it's either or, so you add them together. I got 10 out of 16, which is 62.5%. And then F2 plants was probably finding an F2 plant not round and yellow seeds. And so since we know what the probability is, since we know what the probability is of getting a round and a yellow seed, so what's the probability of not getting that? All we have to do is take 1 minus the 9 over 16, which you get 7 out of 16, which is about 43.8%. Problem 2 states, suppose Mendel across a true breeding tall plant with purple flowers, the true breeding dwarf plant with white flowers. Tall and purple are dominant, while dwarf and white are recessive. F1 generation plants are allowed to self-fertilize and produce F2 plants. And so it's asking for the probabilities here again. And so I designated a key up here. Big T is equal to tall. Little t is equal to dwarf. Big F is purple and little f is white. And so I have my parent generation, which requires a true breeding dominant with a true breeding recessive. And then this F1 generation is allowed to self-fertilize and produce these phenotypes down here, or these genotypes / phenotypes down here. Same thing as the previous problem. And so probabilities, probability of an F2 plant that's tall and purple. So we have the first four. So the first four children, what are the probability of them being tall and purple? And so we go here to the key and figure out that the 9 out of 16 of them are going to be tall and purple according to their genotypes. And so all you do is raise that to the 4, or take 9 divided by 16 times 9 divided by 16 times 9 divided by 16 times 9 divided by 16, and you get about 10%. And then part B asks, what is the first four are tall and what is the probability of the first four are tall and white, or either tall and white or dwarf and white? And so the first four, you have to figure out the probability of each. So you have to figure out the probability of tall and white. So tall and white is going to be right here, big T, little f, and then big T, little f, and that adds out to 3 out of 16. And then dwarf and white, which is this genotype right here, little t, little f. And so what you do is you add those together, because it's an either or problem, and you raise that to the 4, and then you come out to get 0.1%. And then oops, sorry about that. And so that's about 7. The 7 produced 3 that are tall and white and 4 that are dwarf and white. And so using this combination formula that we learned in the lesson, we took 7. There's 7 total factorial, which is factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1. So basically you just take factorial means it's like 10 times 9 times 8, 11 times 10 times, you just keep going down. And so 7 factorial, and then you have 3 tall and then 4 dwarf. And so you do 3 factorial out of 4 factorial times 3 factorial times 4 factorial. And then you go to the probability of getting a tall and white. The probability of getting a tall and white is 3 out of 16. And since you want 3 of them, you're going to raise that to the 3rd. And then for dwarf and white, there's only 1 out of 16 probability you're going to get that. So you have to raise that to the 4 because you want 4 of them right here. And so that's an equal 3.52 times 10 to the negative 4%. And so we want the following order of the phenotype. So we want the first one to be tall and purple, the second to be dwarf and white, the third one would be tall and white, the fourth to be tall and purple, and the fifth to be dwarf and purple. And so basically I found the probabilities of getting a tall and purple, which is 9 out of 16, and I found the probabilities for each one of these according to this key, and then using this key to determine out phenotypes. And basically what I do, since each child is independent from each one, you take the first one times the second one times the third one times the fourth one times the fifth one, and it comes out to 0.0695%. Problem 3 states, a cross was made between true breeding strains of plants that are agriculturally important. One strain is disease resistant but herbicide sensitive, and the other was disease sensitive but herbicide resistant. A plant breeder crossed 2 plants and allowed F1 generation to self-fertilize. The following data was obtained. F1 generation, all offspring were disease sensitive and herbicide resistant. F2 generation, you have 157 that were disease sensitive. Disease sensitive, herbicide resistant, 57 disease sensitive, herbicide resistant, or sensitive, 54 disease resistant, herbicide resistant, and 20 disease resistant, herbicide sensitive. And so basically I drew a key right here, and it asks us to come up with a null hypothesis. So null hypothesis is that these 2 traits will exhibit Mendelian genetics of a loss aggregation of independent assortment. And so you have the parent generation, you have a true breeding dominant and a true breeding recessive, and it gets you to F1, which is a point where they're sensitive, they're disease sensitive, but herbicide resistant. And I do the F2 generation right here using the fork line method because it was easier and faster. And then I use the chi-squared value. So that's just to find the chi-squared value. So this is the equation. And so you have your expected probability of getting a disease sensitive. So I figured out the expected value of and then the observed values of a disease sensitive, herbicide resistant, disease sensitive, herbicide sensitive, and the expected value for disease resistant, herbicide sensitive, or resistant, and then disease sensitive or disease resistant, herbicide sensitive. And then I have the observed values in the table shown right here. And so basically, I'm using this formula, putting the observed value here and then the expected value in here for each one of these. So this particular part right here is independent from this one right here. And so just these two numbers are going to go into here. So you have your observed minus your expected squared over your expected. And then since it's a summation, you're going to add them all together. So you're going to add this to this and then this to this. And that's going to come out to 0.543. And so it fails to reject the null hypothesis. These traits do follow Mendelian genetic patterns. And so the following pedigree for problem 4 is the following pedigree charts were analyzed. And so this one is an autosomal dominant. It's an autosomal dominant because of these particular traits right here. And so this guy has to be heterozygous, as long as with these children right here, but these guys have to be recessive. And so, and how I kind of figure this, how I kind of determine it was dominant is because when you have dominant, you have a 3 out of 4 possibility that one of your children is going to exhibit the trait if it's autosomal dominant. And here, more than half of the children, same right here, more than half the children are exhibiting the trait. And same thing with right here. And so that's how I was able to determine if it was autosomal dominant or not, especially this person right here. For this one, you have X-linked dominant. So what I did is I drew a little table right here. So I just wanted to be X-linked dominant. And so how I did that is I just did a generic big A, little a. And so I did it right here. And so I came up with a probability of like about half your children are going to have the trait, which is very true in this case. About half of these guys' children do have the trait, especially half the men are going to have the trait and half the women are going to have the trait. And then right here, I did the same thing where since she doesn't have the trait, she's recessive, and since he has the trait, he does have the link. And so as I did the cross, I noticed that all the daughters had the trait, which is very true in this case, that all the daughters are exhibiting the trait. So that's how I determined to be X-linked dominant. This one turned to be X-linked recessive, and so basically he has to be dominant because he's not exhibiting the trait, but she has to be a carrier. And so what I noticed is that it kind of skips generations, which is a very characteristic thing of this particular trait. But she must have been she has to be completely dominant, because if she wasn't, then these children would have to have the trait. And so then I figured out, look, well, he has to be recessive, so X little a. And so I did the cross right here, and so I determined that all the sons have to be dominant, which they can't exhibit the trait, which they don't exhibit the trait. None of the sons exhibit the trait, so I determined to be X-linked recessive from there. And then for this last one, I determined to be autosomal recessive. Both these parents have to be heterozygous in order to at least get one child that's recessive, according to this little chart that I drew up right here. And then I determined that if she also has to be recessive, because if she was dominant, then none of her children or none of her descendants would ever exhibit the trait. But eventually it gets down to a point where this particular child exhibits a trait, and so he has to be little a, and he has to be big A, little a. And so there's a 2 out of 4 possibility that the children will not exhibit the trait. And then same thing here, this person has to be heterozygous and this person has to be heterozygous. And so it happens to be like only 1 out of 4 times this child is autosomal recessive. And so